For over 100 years, there's been one rule in physics that has felt totally absolute, like a universal speed limit that nothing can ever break. But is that really true? We're about to dive into a question that has fueled tons of science fiction and even stumped some of the most brilliant minds on the planet. It seems like a simple question, right? A straight yes or no. But the answer, well, it's a fascinating journey through optical illusions, the mind-bending expansion of the universe, and the just downright spooky nature of reality itself. So to start, we've got to understand the rule before we can even think about how to break it. And that rule comes from Albert Einstein and his theory of special relativity, which basically sets a hard and fast speed limit for our universe. Okay, so the cosmic speed limit is c, the speed of light in a vacuum. It's the mandatory travel speed for anything without mass, like photons, the particles of light. But here's the thing, for anything with mass, it's a finish line you can never ever cross. Why? Because the faster you go, the more massive you get, which means you literally need an infinite amount of energy to actually hit light speed. It's just not possible. But here is a really crucial way to reframe this whole idea. The speed of light isn't just about how fast light can travel. It's the fundamental speed of cause and effect. It sets the limit for how fast any event can possibly influence any other event. That's the real barrier we're up against. So, with that rule firmly established, let's look at some things that look like they absolutely shatter it. These are cases where our eyes and sometimes even our best telescopes can be totally tricked. All right, here's a classic thought experiment for you. Imagine you have this ridiculously powerful laser pointer and you shine it on the moon. Now, if you just flick your wrist really fast, that little red dot seems to zip across the entire lunar surface at a speed way, way faster than c. So did we just break physics? Well, not quite. The crucial point here is that no single thing is actually traveling from one side of the moon to the other. Every single photon in that beam still travels from your laser to the moon at exactly the speed of light. The dot you see is just a series of brand new photons arriving one after another. It's an idea, a pattern. It's not a physical object breaking the law. And this exact same principle applies to a whole bunch of other illusions. Think about a shadow you cast on a faraway wall, or even those massive jets shooting out from distant quasars that look like they're moving faster than light. They're all just tricks of perspective. In every single one of these cases, no actual information or matter is breaking that cosmic speed limit. But what if the speed limit isn't broken by something moving through space, but by space itself? This is where we find a genuine, absolutely mind-bending exception to the rule. Yeah, you heard that right. The universe is expanding, and this expansion is literally carrying distant galaxies away from us faster than light can travel. In fact, most of the galaxies we can even see are already doing just that. So how on earth is this possible without totally violating Einstein's law? The key is to get the difference between moving locally and what's happening globally. See, special relativity applies to things moving through space-time, but these galaxies aren't firing up some massive engines and flying away from us. Instead, the very fabric of space-time between us and them is stretching. Locally, right there in that galaxy, no laws are broken, but globally, the total distance between us and them grows at a superluminal rate. Wild, right? Okay, so we've seen illusions and we've seen a cosmic loophole, but now things are about to get truly, truly weird. We're heading into the quantum realm, which is home to maybe the strangest faster-than-light-related phenomenon of all. We're talking about quantum entanglement. So imagine two particles are created together and become linked. From that moment on, they basically share a single existence. If you measure a property of one particle, like its spin, you instantly know the matching property of its partner, even if that partner is all the way on the other side of the galaxy. Now, a common way people try to explain this is the pair of gloves analogy. If you know you put one left and one right glove in two separate boxes, the second you open one box and see the left glove, you instantly know the other is a right glove. But here's the thing, that analogy is actually wrong. It suggests the information was always there, what physicists call a hidden variable. But experiments have proven that's not what's happening. The quantum reality is so much stranger. The particles don't have a definite state until the moment you measure one. The act of measuring one particle instantly defines the state of the other, faster than light. This instantaneous connection is so bizarre that Einstein himself couldn't stand it. He famously called it spooky action at a distance. It just seems to fly in the face of that whole speed of causality thing we talked about. And action here seems to have an immediate effect way, way over there. So this leads us to the ultimate question, of course. If you can instantly affect a particle light years away,
Can you use that to send a message? I mean, could you manipulate one particle to transmit, say, Morse code to its twin?
And the answer, maybe a little frustratingly, is no. There's something called the no communication theorem that explains why. While the results of your measurements are always perfectly correlated, they are also individually random. Think of it like this. You can't force your particle to be spin up to send a 1. You can only measure it, and you'll get a totally random result, either up or down, 50-50 odds. Your friend light years away will instantly get the opposite result, but because you couldn't control your initial outcome, you can't actually transmit any useful information. So, it seems like the cosmic speed limit is remarkably tough to break. Illusions are just tricks of the eye, cosmic expansion is more of a loophole in the wording of the rules, and even that quantum spookiness can't be used for communication. So, where does that leave the dream of faster-than-light travel? I think this quote just sums it all up beautifully. Physical objects with mass are absolutely bound by the speed of light. But concepts, patterns, geometric effects, and even the fabric of space itself are not. And that's the core distinction we have to remember. Of course, that hasn't stopped theoretical physicists from dreaming big. You've got concepts like the Alcubierre warp drive, which would basically squish space in front of a ship and expand it behind. You have wormholes that could act as a shortcut through space-time. The problem? They all seem to require something called exotic matter, stuff with negative energy or negative mass, which we have absolutely no idea if it exists, let alone how to make it. And then you have tachyons, which are purely hypothetical particles that would, by their very nature, always travel faster than light. But maybe the most radical idea of all is to question the rule itself. Some physicists have proposed that the speed of light might not have always been a constant, that in the super hot, super dense early universe, c could have been way higher, maybe even infinite. And this isn't just some wild guess. It's a testable theory that makes specific predictions about the cosmic microwave background that we can actually go out and look for. And that leaves us with one final, really tantalizing thought. Is the speed of light a truly fundamental, unbreakable law of nature? Or is it more of a local bylaw, just for our particular cosmic neighborhood and our particular time? The final answer is still out there, waiting for us to discover it. Thanks for exploring all this with me.